Okay, so welcome back. So this is fourth lecture. So in the last class, we started classical cryptography, especially these ciphers, the early days ciphers. So continuing that journey, I'm going to give you 2, 3 more examples of ciphers today. And later on in the next class, I'm going to do cryptanalysis, which is very, very important for some of these ciphers. Okay, so we talked about so again just recalling. So our crypto system is 5 tuple. P is set of plain text, C is set of ciphertext, K is set of key space, and E is encryption rule, and D is decryption rule, right? And we should have this compatibility between encryption and decryption. Okay. We talked about shift cipher. So encryption rule was, X plus K, where K is fixed from the key. Okay. And decryption is Y minus K. So if you add some things, you have to subtract the same thing, right? Then we talked about substitution cipher. So I gave you an example there. So we stopped at this point last time. So I hope you are able to decrypt it, right? If not, you can still write some computer program to do that. Anyway, so now the first cipher that we want to discuss today is affine cipher. Affine word is used for this, linear thing. So A and B are elements of Z26. Okay. So the pair A comma B acts like a key, and then encryption is, so if X is our plain text, AX plus B modulo 26. Okay. This is the affine combination. So that means, if we do this, we should know also how to recover it, right? So the recovery is also important. The decryption should be there. Now, in order to do the decryption, you need to, so if AX plus B is equal to Y, something is computed, Y is there. So Y is given to us, and I will ask you what is X. You should be able to solve this equation, right? Now, if you want to solve this equation, certainly this equation has a unique solution for X. Okay. And now, rather than solving this Ax plus B congruent to Y mod 26, in fact, I can say that, so I can take, B on the right side. So Ax should be congruent to Y minus B mod 26, right? So essentially, we should know a technique to solve this equation. Ax is congruent to Y mod 26. Something like this, right? I'm just replacing the same thing with Y, just to say that we should know how to solve this. Okay. And I think this is important. So this we can solve provided A inverse exists. Okay. Then only we can divide to both sides, right? So we need to count how many times A inverse exists when we do integer modulo M. Okay. So I'm going to discuss this. Now, one thing I should mention here is there is a relationship between substitution cipher, affine cipher. So as you can see that affine cipher is the generalization of shift cipher. So if we put A is equal to 1, we get shift cipher. Right? These kind of relationships are there, which is straightforward to observe. So people are just trying to do. So basically, this is affine cipher is a better thing. So we can look at in general what is affine cipher and how do we do the encryption decryption. Okay. Now there is this observation that the equation Ax congruent to Y mod 26 has a unique solution for every Y if and only if GCD of A comma 26 is 1. I think you by now you have this feeling why it will be true, right? So whenever this GCD is 1, then only we can find a unique solution. In fact, why we restrict ourselves to 26? We can say the same thing for even if we take modulo M, right, in general, apart from 26, right? So the equation Ax congruent to B mod M has a unique solution X in integer modulo M for every B in Zm if and only if GCD of A and M is 1. since this is an interesting fact, and as a young mind, what you want? A cup of tea, and you can observe this, right? Try a couple of things, right? And then see how do we prove it. I'll just do one part. I'll say that this is if GCDs of A and M is 1, obviously this is a unique solution. Suppose there are two solutions, x1 and x2, right? Then that means what? AX1 congruent to B mod M and AX2 congruent to B mod M. That means AX1 is congruent to AX2 mod M. That means A times x1 minus x2 congruent to 0 mod M. And this implies that M will divide this quantity. That means M will divide this quantity provided GCD of A and M is 1, which will be true anyway. And that means x1 is congruent to x2 mod M. So this is a unique solution, no doubt about it, right? So the other part, I'll leave it to you for a t time problem. Suppose x is in Zm, right? Then you need to observe that Ax takes on M distinct values mod M. Okay, so I think you can try that. So I leave it to you. So basically, this is an interesting fact that if GCD of A and M is 1, then we have this equation has a unique solution. Now, I already talked about this Euler torsion function phi. So I can now formally say that for any m greater than or equal to 2, which is the integer, and A is greater than or equal to 1, if GCD of A and M is 1, we call it formally as that A and M are relatively prime. Okay. And the number of integers in Zm that are relatively prime to M is denoted by phi of M, Euler torsion function, right? Okay. Now, if M is prime number, I already told you that phi of p is 1 minus p1 because phi of p is p minus 1 because 1, 2, p minus 1, everyone will have GCD 1, right? 1, 2, 3 because it's a prime number, right? In general, we have this formula: if M is a product of pi raised to power ei. This is because of fundamental theorem of arithmetic. You might have, you might recall that, right? Any integer m can be written as product of prime powers, right? It's a very powerful theorem, and so phi of m is partial product. So pi raised to power ei minus pi raised to power ei minus 1. This is the formula to compute Euler torsion function in general, right? Pi's are distinct primes and ei's are positive. Okay. Now one can ask, how many keys are there in the affine cipher? So we know, and affine cipher is AX plus B, right? AX plus B. So A and B we need to choose the pair. How many ways we can choose A and B? B can be chosen in any m ways, right? And A can be chosen such that GCD of A and M is 1. That can be done in 5 ways, Euler torsion function, right? So that means total number of keys are M times 5m, right? So those many keys will be there. Okay, and I think you can, again as an example, what will be phi of 60? Product of prime numbers, right? Which is 2 square minus 2, 1, right? For phi of 2 square will be something like this from that formula, times phi of 3 is 3 minus 1, and phi of 5 is 5 minus 1 because 3 and 5 are prime numbers, right? So phi of p is equal to p minus 1. Using that formula, you can compute. I hope it is correct. So 2 into 2 into 4, right? Okay, so you can compute it, right? So it's a simple formula. Euler torsion function is a beautiful function, right? Because you can do, it counts many beautiful things, right? So this is just one of them. In fact, if I ask you a question, what if x into y, how many pairs x comma y are over Zm such that GCD of is 1, right? That is also, it will involve something like this kind of function. In fact, some of your seniors have recently discovered new integer sequences. If you remember, you saw that post which I posted, right? So they have discovered by counting these kind of things. In fact, they have found a generalization of Euler torsion function in a nice way. All your young people, right? So by drinking cup of teas, you can obtain different things. So, okay, so essentially A is in Zm if and so basically an element of inverse exists if and only GCD of AM is 1, right? I mean, this is the condition. So now you should memorize this. For example, in Z4, you know that inverse of 1 is 1, inverse of 3 is 2, and 2 inverse does not exist, right? So because GCD of 1 and 4 is 1, and GCD of 3 and 4 is 1. So there are two of them, and GCD of 2 and 4 is 2, which is not 1. So 2 will not have an inverse, right? So it's easy, interesting observation to remember that in integer modulo M, inverse of an element exists if and only if GCD of A and M is 1, right? And we should know how to count these kind of things, right? That is very, very important. Okay, so now we return to the Supine cipher. So y is equal to ax plus b mod 26. So that means ax is congruent to b minus y mod 26, right? Now if GCD of A and M is 1, so x will be A inverse b minus y mod 26, right? It's a very straightforward calculation. So this is how we can decrypt. So now we have the full system here, the affine cipher. So P plain text, cipher text are on Z26, right? And our key is this pair A comma B, because AX plus B is our encryption rule, right? Such that A is in Z26, B is Z26, and I'm also putting this condition that GCD of A in 26 is equal to 1, because we want the inverse of A should exist, right? So for a typical pair A comma B in this key space, encryption rule is AX plus B mod 26, and decryption rule is A inverse Y minus B mod 26, where X and Y in Z26. So this is the complete system for affine cipher, right? Any question? Fairly straightforward, simple, high school mathematics, right? So maybe sometime you can give a lecture to high school students about this encryption. They will enjoy, right? Now, as an example, suppose k is equal to 7 comma 3, right? So we know that what is 7 inverse mod 26 is 15. You can compute that anyway. So encryption rule is 7x plus 3. Decryption rule is 15 times y minus 3. 15 is inverse of 7, right? So we have 15 times y minus 3, right? So that means, and of course, you can note that this encryption decryption rule should be satisfied, right? Encryption after encryption, you do the decryption, you will get the same thing, right? So if you take plain text as hot, H is 7 by that mapping 0 to 25. This is 14, O is 14, T is 19. So you can compute 7x plus b in each case. So 7 will be 7 into 7 plus 3, 52, right? 52 modulo 26 is 0, right? So you will get 0. And the next one is 23 and 6, right? So this is the encryption thing, and then so you again map it back to the alphabets. You will get AXG. This is the cipher text, right? And decryption is easy. Similarly, just compute the inverse, right? I mean, inverse we have done anyway. So just you need to compute 15y minus. So for each of these things, so once you receive this, you can just compute, go back here and just do the reverse, right? 15y minus 19. So you can see easy exercise, right? I have left it. You can calculate this, right? To get the actual answer. Okay. This is another beautiful cipher. Okay. So it's known as Vigenere cipher. It's kind of generalization, you see. M is a positive integer. Plain text and cipher text are, and key space, all are in Z26 raised to power M. Now they are, you are looking at them as a vector. Okay. Vector of length M. So key is so K1, K2, Km. So encryption of, if you have a vector x1, x2, xm, encryption is x1 plus k1, x2 plus k2, and so on, xm plus km. And decryption, so if y1, y2, ym is received, so decryption is y1 minus k1, y2 minus k2, and so on, ym minus km. All the operations are in integer modulo 26, right? Very simple, just generalization, right? Now, in fact, the cryptanalysis is very interesting. I'll talk about it in the next class. Yeah, probably next class or whatever, maybe after that. So Here is an example. So this key vector, normally we call it as a keyword. Okay, keyword for encrypting. So if m is equal to 6, then suppose keyword is cipher, CIPHER. So you can map it to 0 to 25. So C will be 2, and I will be 8, P will be 15, and so on. So we have 2, 8, 15, 7, 4, 17. That is our key vector, right? And if the plain text is this crypto system is not secure, you can map everything to alphabets, right? So we have 19, 7, 8, and so on, everything up till 17. Now you add this, so basically, no, sorry, from 197 up to 24, and the second thing is from here, 18 to whatever is the last number, 2 actually, yeah, and then up to 15. This is the whole thing, okay? So the first row is like this, corresponding mapping, right? Now key is of length what? 1, 2, 3, 4, 5, 6, right? So this is the key, 2, 8, 15, 7, 4, 17, right? Then again the key, 2, 8, 15, 7, 4, 17, like that. You decompose into blocks, right? So we have all the keys up to this place, right? So 2, 8, 15, 7, 4, 17, like that, right? So you have the whole key, and then you just add them and do modulo 26, get the resultant, corresponding thing. So what will be the resultant? I can show you. The encrypted text will become this, right? So, which is okay. The question is, how many possible keys are there? K1, K2, Km, each will have m choices. How many will be there? 26 raised to power m, right? Sorry, yeah, each will have 26 choices, right? So 26 raised to power m, okay? And this number is large because for m, even for m is equal to 5, this is more than 1.1 into 10 to the power 7, right? So we always worry about EKS. What is EKS? Exhaustive key search. That word you need to keep in mind. EKS should be infeasible whenever we are making a crypto system, right? So that you cannot exhaustively list all the cases and you should not be able to search it, right? So EKS is very, very important thing. No, its inverse is in terms of negative, right? It's not. Yeah, 0 to 25. So we are talking about key. So K1, K2, Km. Each K1, so K1 has 26 choice, K2 has 26 choice, and Km has 26 choice. No. There is no need to worry about inverse here. See, because there is no operation of A inverse, right, here. It's very simple, it's addition. Operation is just addition, no inverse here, right? Okay. This is also another interesting cipher known as Hill cipher. So we'll talk about the cryptanalysis of all these crypto systems later on. How do we actually just looking at the frequency of the things and you can try to break the system. It's a beautiful thing. Okay. So now Hill cipher. So this involves matrix. How many people of you are very good at linear algebra? Linear algebra is very beautiful, right? No matter where you go, what problem you do, whether it is machine learning, Phala learning, right? It will lead to system of whether you are searching anything on Google, it will lead to system of equation AX is equal to B, and you analyze that system, right? And since you know that, I love things which are over finite fields. So linear algebra becomes more beautiful. And then you go to finite rings, it becomes more beautiful, right? So I can always ask you interesting questions there, right? So I'm going to ask you a few things here. Anyway, so it's now here, the plain text is x1, x2, xm in P. K is a m by m matrix, okay? So Kij m by m matrix, okay? And so encryption rule is, so we are getting encryption of x is a vector here, y1, y2, ym, which is take this vector x multiplied with this matrix K, okay? So there is a vector of length m multiplied by m matrix. You will get a vector of length m, right? Matrix multiplication, you know, I hope, how to multiply two matrices, right? By the way, you should always ask a question. So, what is the fastest algorithm for multiplying two matrices? Any idea? Recently, last year, machine learning has discovered another fastest algorithm, right? For matrix multiplication. Search karna, right? That's up to you. Anyway, so we have this thing. Now, K, capital K is all m by m invertible matrices over Z26. That's our key. So basically, this K is our kind of key, right? So basically, we have encryption. Rule is encryption of X is X times K. X is a vector here, remember? And decryption is Y times K inverse. Provided, remember, we are working over Z26. Not every time inverse will exist, right? So the question that can be asked for your T time is, how many invertible matrices are there? So over Z2, can you count? Or Z3? I can give you some hint. So suppose we are working at m is equal to prime, right? M is prime number. That means we are working over integer modulo p. And I want to fill a matrix, say m by m, which is invertible, right? Over ZP. So P cross P matrix essentially we are looking at, because m is equal to P I am taking. Now, how many invertible matrices are there over ZP? How will you do that? So if you know a little bit of linear algebra, so you know that matrix will be invertible if determinant is non-zero, right? And determinant is non-zero provided all the rows, because this is full matrix, or columns, or if rank is full, right? Rank, you remember, row rank or column rank, maximum number of linearly independent columns or maximum number of linearly independent rows, right? So that should be full. That rank should be full. Rank full means, so now if I have to count these matrices, what I should do? I take a m by m matrix. I fill the first vector. So first vector is a vector of length p, right? If I'm filling p by p matrix, each entry is over ZP. First vector, I can choose any non-zero vector out of ZP, right? So ZP, how many possibilities are there for one vector? Each one has p choice. How many will be there? So I am choosing one vector. First entry is in ZP, second entry is in ZP, third vector is in ZP, and last entry, pth entry is also in ZP. How many choices are there? P raised to P, right? But I am avoiding zero vector, so you delete that. So choices are left. P raised for P minus 1 for first vector, right? Got it? So first vector can be chosen. I'm just looking at the column vector. I mean, you can do column or row, whatever. I'm just fixing our frame of reference is a column vector. So first vector can be chosen in these many ways. Now I should choose a second vector such that second vector is not dependent on the first vector. Right. Now the second vector could be dependent on the first vector in how many ways? So if first vector is, say, alpha, second vector is beta. If alpha is lambda times beta, where lambda is scalar in ZP, those many times it will be dependent, right? So independent ways will be total ways minus this number, right? P. So P ways it will be dependent. So this minus this number, right? So P raised per P minus P, right? So like that you can count. Now you choose the third vector. Third vector should be chosen in such a way that it is not a linear combination of first two vectors, right? Lambda 1 and lambda 2, right? So lambda 1 and lambda 2 are the ways in which it can be dependent. I'm just giving you line of thought. Rest you can determine by drinking tea. To complete this statement, right? How to figure it out? How many invertible matrices are there? Now this case is still simple because I'm just taking it integer modulo p, because everything is field. It's very easy. Now just lift the bar a little bit and we go to integer modulo m. Then there will be more difficulty. थोड़ा और चाय चाहिए, coffee चाहिए, right? So, so basically, because, but anyway, I'll give you the condition here. So first give an example, then I will talk about it more, about the inverse thing. So if K is 11, 8, 3, 7, 2 by 2 matrix, M is equal to 2 here, right? Sorry, that size is 2 here. Now inverse of 11, 8, 3, 7 is 7, 8, 23, 11. So modulo 26, provided inverse exists. How to find the inverse? That's another question. See, there is a one very famous thing, right? जहां ना पहुंचे रवि वहां पहुंचे कवि, right? So, so basically, algebra is very powerful. You can assume that something you don't know, call it x, put it there, solve for x, right? So you can always say that, okay, I want to find the matrix 11, 8, 3, 7 inverse. Take 11, 8, 3, 7 times A, B, C, D, 2 by 2 matrix, put it equal to 1, everything modulo 26, solve the equation for A, B, C, D. That is a very easy thing to do, right? You can always find the inverse like that. But you should know how to solve the equations over the finite rings. That's another daunting task. I would say it's a beautiful task, right? So you enjoy that. Anyway, so assuming that you know how to find this inverse, so you know that 11, 8, 3, 7 times this is equal to 1, 0, 0, 1, right? So it should be 2 by 2 identity matrix, right? Right. So you know the thing. I mean, you can check that when you multiply this into this, modulo 26, you will actually get 1, right? And so on, all the other entries, right? So finding inverse is an interesting task and beautiful task anyway. So if you want to develop linear algebra over Z4, you can contact me because I spent a lot of time there, over Z4. I can show you different things here. Anyway, so if you have plain text July, G-U-L-Y, so J-U, where? You mean to say it's not working? I mean, I don't know, you can check it. But how you're computing inverse? Directly that adjoint matrix and so on and so forth? But remember, everything is over Z26. So, whether everything will work, I should tell you, normally over fields, you can do row reduced echelon form that does not work over rings. Okay. So row reduced echelon form does not work over ring. Things are a bit bizarre, right? Things are different. So I'm just telling you, yeah, I mean, you need to do it somehow. And anyway, I will tell you more details about how do we do this. We can spend a lot of time there. In fact, I'll give you the condition right now. Okay. So we have July, JU goes to 9, 20. Why we are breaking into? Because the key is 2 by 2 size, right? And then we have LY 1124 from the mapping. So then 920 times this matrix, we get 3, 4, and the second one we get 1122. So when combining them, we get DELW. So this is our ciphertext, DELW. His cipher is pretty straightforward, except that you should know how to find inverse, right? Because that is important for decryption. So obviously there should be some condition. We need to have some condition when the inverse will exist, okay? So again, you will see that it's a similar the one which we saw earlier. A matrix K has inverse modulo 26 if and only if GCD of determinant of K and 26 is 1. Right? I have told you the result, but I have not given you any proof. So what you need to do? Drink cup of tea and or coffee and try to establish this fact, right? When this will be true. Essentially, this condition is saying that I'll tell you how to think about it. this condition is telling you that, you see what happens when you look at any matrix, I mean any matrix which is non-singular over finite over field, whether finite field or field, you see the determinant is non-zero. That's what we look at, right? Means the inverse should exist, right? I mean non-zero. Here the condition replaces to determinant should be unit. Unit over the rings, it should be unit. Unit means invertible. I mean, right? So that number should be invertible basically, right? So that condition comes automatically. So that's why this GCD condition is there anyway. Okay. So it's a very interesting condition. So basically, if this condition is satisfied, so basically when we are making this Hill cipher, we'll put this condition. Otherwise, we cannot use it, right? Because the inverse will not be there, then the crypto system will be of no use. So this is something is important thing, right? When we make the crypto system, I think, yeah. So this provided K inverse exists, here we are saying that GCD of determinant of K and 26 is 1. That condition is there, okay? Then only the inverse will exist, okay, over Z26. Okay, so I think this is a very important thing that you should play around with the inverse business, and maybe you can come up with a new algorithm, who knows? You people are young people. So, okay, just you have to keep the phone aside, okay? Get a comfortable chair, get a coffee, cool breeze outside, and do calculations, right? So, okay, another one is permutation cipher or transposition cipher. So if I'm just taking m is equal to 6, so if x is 1, 2, 3, 4, 5, 6, permutation is a function, right? I hope you know that thing in the linear algebra, no, algebra probably, yeah. So pi of x is this permutation. 1 goes to 3, 2 goes to 5, 3 goes to 1, 4 goes to 6, 5 goes to 4, and 6 goes to 2. So this is a permutation function we can write. And then we can find the inverse permutation, right? So when you pi into pi inverse is how much? So it will be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, right? 1 goes to 1, 2 goes to 3, identity permutation, right? So permutation group you might have heard. Some people who are very good in maths and computing, they are doing maths and computing courses, right? So they must be knowing abstract algebra, right? Okay, so this is something interesting. So anyway, so encryption and decryption can be done like this. Let me show you an example of this. If m is a positive integer, our space, plain text, and ciphertext is Z26 raised to power m. Okay, we are looking at the vectors, and k is all permutations of 1 to m. So for a key pi is a permutation function. E pi of x1, x2, xm is x pi 1, x pi 2, x pi m. You're just applying that permutation, right? And decryption is just inverse permutation. Okay. Now, interesting thing to note. This is a special case of Hill cipher only. Can anyone tell me how? You saw Hill cipher that the vector is there multiplied by k by matrix, and then you m by m matrix, and you get output, right? How this is so we are claiming that this permutation cipher is a special case of Hill cipher. Yes. Yeah. So permutation matrix. Yeah. So you can find the permutation matrix. You might have seen those things while finding inverse, right? You have done those calculations in linear algebra, right? Good. So basically, each permutation corresponds to a permutation matrix, right? And so essentially, the whole business becomes multiplying with the permutation matrix, right? So that is why it is a special case. I will give you an example in this case. What happens here? Anyway, so if the plain text is this, you divide into these things and apply permutation pi. So whenever we are writing bigger ones, bigger alphabets, this is encrypted text. That is a plain text, right? So we are just applying the permutation pi in the blocks, right? So here is the permutation matrix. So we are talking about this permutation. So by the way, the permutation is this. Can anyone tell me how to get this permutation matrix? So this is the permutation, right? You take the identity matrix and apply the same permutation there. You get the permutation matrix. If you are, if you can recall all your linear algebra, probably linear algebra class, yeah. There they teach, right? How to get permutation matrix from a permutation. So what you do, for example, here the permutation is 1, 2, 3, 4, 5, 6, 3, 5, 1, 6, 4, 2. So take a 6 by 6 identity matrix, apply this permutation there, okay, and you get the matrix. Similarly, we have the inverse matrix. So I think here is the example. For this pi, here is the permutation matrix. Okay, permutation applied. This should be the first row, right? And so on in the identity matrix. You apply the permutation. So the same permutation you apply to the rows, right? You get the permutation matrix, right? You can also get the column matrix, also the same definition, but this is how you get. So basically, definition is k pi is kij. So ijth entry is 1 if I is permutation of j, right? And 0 otherwise. And you can get this permutation matrix, right? So essentially, permutation cipher is a special case of Hill cipher. And so Hill cipher, everything else is fairly straightforward except that computation of inverse, right? And that condition, the DCD of determinant of k and 26 should be 1. Why we have that condition? So why I am asking you to do these T-type problems? Because you will get a habit of developing algorithms, because this is very, very important, right? Baki to, everything is the source code is available somewhere, library, Python, blah, blah, and you just use it. But if the library is not available, what will you do? Unless you can think about these things, you will not be able to write. So then there is a limitation. Okay, when you are doing some projects, actually, remember, in any computer science application, couple of things are very, very important. One is which algorithm to choose, right? Reduce the complexity, right? That's another thing, very, very important aspect, right? So there may be an algorithm working perfectly fine, but the complexity is too high, so people will not use it, right? It should be efficient, right? So basically, then you can also look at time complexity and many other things, so that actual product can be built, right? So you really should have this habit of trying to do these small things so you can think about the problems. And this habit you should have. Just you need a cup of tea, right? By the way, Donald Knuth book, how many of you have read now? I told you in discrete math class, right? The art of computer programming? Not a single one. I told you that if you have read that book, you go to your competitive programming interview, the person will be afraid of you, right? So you say that I have read, you just say one thing, right? I read Donald Knuth book, so please ask questions from there. So he will never ask, right? So that is the thing, right? So that's the beauty. So you should look at it anyway. Anyway. Oh, I think stream ciphers we will talk about later on, maybe. Because it's a totally new way of thinking. I don't want to mix everything. So what I should suggest now, you should certainly, I think I want people, you should know how to find the inverse of a matrix over integer modulo m, how to count them, right? So please do send me the solutions, or you can post it on the WhatsApp group, right? And so you should be in the single frame of mind while handling this stuff, right? I'm telling you, it's really beautiful. By the way, I should tell you that over integer modulo 4, for example, which is very special case, right? It's a ring, right? 2 into 2 is not equal to 0. I mean, sorry, 2 into 2 is equal to 0. None of them is 0. Even in there, row rank is not equal to column rank of a matrix. So normally you see that row rank is always equal to column rank, but here that is not the case. Row reduced echelon form does not work, right? But there are ways to handle those things. Okay, it's really interesting. So basically, you know, these days, why I'm saying that, if you are, for example, suppose you are looking at fully homomorphic encryption. Have you heard of FHE? FHE is very, very important, you know, to provide privacy, right? So you can do you can do operations on encrypted data, right? So there, these ring business and field business is going to play a very important role if you really want to understand. I have seen people, I mean, I have seen even students. I'm very good programmer, I can do anything. But when they want to look at the thing, this algebra ka kahan se beech mein aa gaya, right? So this field and ring is very, very important if you really want to understand these algorithms, right? Okay, so please do get a habit, and you don't have to worry about it. It's a beautiful thing, actually, right? Just take a cup of tea and then enjoy. I think that's all. Tomorrow I will talk about stream cipher.